Okay, so in the previous lecture we discussed the another proof of Brook's theorem, and using basically color switching. And this is a very useful technique when we work with coloring questions, and it gives you a very different perspective. See, the reason we are looking at different proofs sometimes is that, like, each proof tells you something new, right? It tells you something about the structures of the the graph, or the question itself. Like, you get a better picture about how these things work out. Of course, there are many other proofs. Interested people can look for them, but we cannot cover too many proofs in this course for the same topic. Okay, now, uh, so what we have already seen about the chromatic number is that the chromatic number is always, at least as big as the click number, right, which is omega. In the click, every vertex should get different colors in a proper color. So, some of the immediate questions that arises is that, when this inequality becomes an equality. It is one question one can think about. Can you say that, like, command number is equal to click number, and when is that the case, right? Then, and we have already answered that, right? When we were, like, not we have not answered, like, we have said that, no, it's actually equal to a number. Yeah. So Brook's theorem says that, like, for complete graphs, of course, we know it is actually equal to this, and for other graphs it is less than or equal to maximum degree. But of course, the chromatic number uh, can be equal to the click number even if the graph is is not a click. For example, you have a bipartite graph, right, where the click number is 2 and the chromatic number is also 2. Right? You have, can you think of other classes of graphs where the click number is equal to chromatic? In fact, one of the questions that I asked earlier, to show that if you have a graph, then, if you have a bipartite graph, then it's complement graph, right? It also has the chromatic number is equal to its click number. This is something that I asked you to prove, and that also tells that, there are other classes of graphs where you have chromatic number which is equal to click. So we will investigate this later. Then another question that we can think about is that how large the difference can be. Like, can the difference between the click number and the chromatic number be quite large? We know that it can be, of course, larger, right? Looking at the odd cycle, for example. But can the difference be very large, right? Instead of, difference of 1 or 2, can it be arbitrarily large? Then another question one can think about is how often the difference is large. Like, is it true for, like, a very small number of graphs, or small section of the graph classes, or, like, is it for a large class of graphs it is actually quite different. So each of these questions have been studied independently, and there are several results on this one can look at, but we will look at a few of them. And like, for the last question, for example, maybe surprising, but that one, it turns out that, like, for almost all graphs, the chromatic number is different from the click number. So when I say almost all, it's like, if you are looking at, all possible graphs generated randomly, like, then with very with probability equal to tending to 1, this will be always different. So now, the second question is what we are going to immediately look at, that how large the difference can be. And we actually show that the difference can be arbitrarily large. Okay? So you can have click size very small and chromatic number as large as you want. There are several results in this direction also. So one of the first constructive results was done by a Polish mathematician called Mycielski. And he basically gives you a way to construct a graph. So suppose you are given a graph without, let's say, triangles. So if you give me a graph without a triangle, with a chromatic number, let's say k, then I will tell you how to construct a graph again without triangles whose chromatic number is k plus 1. So you can keep on doing this, right? That graph is also triangle free. Then I can keep on making the large graph graph larger and larger with chromatic number increasing. But again, there is no triangle, which means that the click size is actually equal to 2. So how do we go about doing this? So this is the construction idea of Mycielski. So he claims that there are graphs with omega of g is equal to 2 and chromatic number is equal to k for any k greater than or equal to 2. Now, this is how it works. So I'm going to tell you how to construct. So take any a graph G and assume that G has no triangles, right? So the shortest cycle in the graph is let's say at least 4 or 5, whatever you want to say. Now, given this graph, what we do is that we are going to introduce new vertices. In fact, if you have a graph with n vertices, I am going to introduce n more vertices. In fact, n plus 1 more vertices. So I will introduce n vertices, each one corresponding to the vertices of V, right? I mean of the graph G, right? So for V1 I have V1 dash, V2 I have correspondingly V2 dash, etc. Vn I have Vn dash, right? And then like I will also introduce a new vertex, let's say W, which is adjacent to all of these new vertices, V1 dash, V2 dash, etc. Vn dash. And how is the adjacency of Vi dash, for example? So in fact, Vi dash is exactly a duplicate copy of Vi. Okay? So which means that the neighbors of Vi dash are precisely the neighbors of Vi, and Vi is not adjacent to Vi dash. So basically, if you have a vertex, that is like V, right? Then I am going to and it has these neighbors. Then I am going to introduce V dash as a new vertex, and whose neighbors are precisely these neighbors of V. Right? I'm basically duplicating the vertex V to V dash. So this I do for every vertex. I get V1 dash, V2 dash, etc. Vn dash. And then what I do, I make a vertex W which is adjacent to all of the new vertices. So here is a picture. So you have let's say this graph, which is the cycle that we started with, right? 1, 2, 3, 4, 5 vertices. So 5 cycle means that you know that you need 3 colors, right? Chromatic number is 3. There is no triangle. Now I'm going to introduce, right? So these vertices, let's say U1 dash, U2 dash, etc. U5 dash. So what are this? What are the neighbors of U1 dash? Precisely the neighbors of U1, right? So U1 dash is connected to the neighbors of U1 are basically U2 and U5. So this is connected to U2 and U5. Okay. So this U1 dash is connected to U2 and U5. And similarly, U2 dash, the neighbors of U2 are U1 and U3. So it will be connected to U1 and U3. Then U3 dash is connected to U2 and U4. U4 dash is connected to U3 and U5. And U5 dash is connected to U4 and U1. So we have introduced all the new vertices and then make a new vertex W which is adjacent to each of these. So the claim is that this new graph is also triangle free if we started with a graph without triangle. So can you see why? Okay, think about this and see why this graph is triangle free. So anyone has a suggestion like why the graph? I mean, I'm not talking about this particular case, but in general. Okay, so let us see. Yeah, so Nishank is saying that consider the case where the three vertices. Not exactly clear what he meant, but yeah. So let me spell it out. So first we observe that the set v dash, or like the new vertices form an independent set. There is no edge between them, right? So there cannot be any vertex. So the vertex W cannot be part of cannot be part of the three cycle, right? There is no triangle involving the vertex W because its neighborhood is an independent set. So that vertex I can roll up. Right? Now I will not have two vertices from the vertex at V dash, right? Because if I have any of these two, because it is an independent set, again it is not possible. Right? So we know that like two vertices from V dash will not be part of any triangle. Right? So then let us take any vertex, in a single vertex, let us say ui dash, right? If I pick ui dash, then can it be part of a triangle, right? So suppose it is part of a triangle, it is only by taking two edges, right? Two neighbors of this, and the two neighbors of this must be adjacent, right? Now, if two neighbors of this is adjacent, then what does it mean, right? If two neighbors of ui dash is adjacent, then it says that if you take UI, right? UI is precisely chosen such that like UI dash. I mean UI dash is chosen such that the neighbors of UI and neighbors of UI dash are exactly the same. Right? So now, if the neighbors of UI dash form there is an edge between them, then neighbors of UI also has an edge between them. Which means that if there is an edge between two neighbors of UI, it's a triangle in the original graph. But of course, we started with a graph which is triangle. So therefore, this cannot happen. Okay. So, so we have an argument that the graph that we have obtained is triangle free. Now we want to show that the chromatic number has actually increased, right? Yeah, first give you the claim that the graph G star obtained by the Mycielski construction from a triangle free graph G is also triangle free, right? So we just proved this, and you can try to formally write it down. Okay. So the second claim is that if the chromatic number of the graph G is k, then the chromatic number of the new graph G star is k plus 1. It's exactly one more than the chromatic number. Now, how do you prove this, right? So, of course, what we can observe is that we have, first of all, we can show that there is a k plus 1 coloring, right? Using k plus 1 colors, you have an easy coloring because, as we mentioned, ui dash is precisely VI dash is precisely a copy of VI, right? So if VI dash is a copy of VI, and Vi and Vi dash are not adjacent, what it says is that the neighbors of Vi and Vi dash are the same. So the set of colors which will appear in the neighborhood of Vi will be exactly the set of colors appearing in the neighborhood of Vi dash. So in this case, since Vi and Vi dash are not adjacent, I can always give the color of Vi to Vi dash also. So if there is a K-coloring of the graph G, I can use those colors appearing on Vi to Vi dash also for each of them. And since Vi V dash is an independent set, there won't be any issue regarding two of them get the same color or not, because it's an independent set. But then to color the vertex W, I can always use a new color because I am using K plus 1. So with a new color, I can color the entire graph. Right? So I know that the chromatic number of G star, right, is less than or equal to K plus 1. Now if you show that it is at least K plus 1, then we are done. Okay. So here is the correctness of Mycielski's theorem. First, if G is triangle free, then and V dot, we know in the graph G star, V dot is an independent set, right? And we observed that at most one of V dot can be in a given triangle, right? We also observed that W cannot be part of any triangle. And now if Vi dash and Vj and Vk form a triangle, then Vi, Vj, Vk also must form a triangle in the graph G, which is a contradiction. So we get that G dash is triangle free, I mean G star is triangle free. And then we have, we have, let's say that, there's a K coloring of G. We have seen that how to give a K plus 1 coloring of the graph G star. G star, yeah, I don't know. Sometimes I have used G star, sometimes it's let's say G star. Okay, so now we need to prove that we how to use at least K plus 1 colors. There is no coloring of G star with only K colors. So is it clear so far? Okay, assuming it is clear. Now let us see what happens if we have a K coloring. So to get a contradiction, we will assume that the new graph G star has actually a K color. Okay. Now we know that we can always rename the color classes. So without loss of generality, we can assume that the vertex W is colored with the color K. So we'll assume that vertex W is colored with color K. Now what does it tell? This says that because W is in the neighborhood of every vertex in V dash, right? The colors that is appearing in V dash can never be in code K, right? So the only colors that are going to appear in V dash are from 1 to etc. K minus 1. Now, of course, in this coloring of G star with K colors, the color K can appear in G itself, right? So there could be some vertices in G which has received the color K. It's possible, right? So let's say that color K is used on some vertices. Now, of course, since we are talking about one color, the set of vertices which are colored with color K must form an independent set, right? Because it's the proper coloring that we are assuming. So there is an independent set, let us call it as K or something, right? Which are colored with the color K, right? So this is a set of all vertices in G, such that color of V in this coloring is actually equal to k, right? So that is the set of vertices. Now I am going to recolor the vertices, in A, right? With colors from 1 to k minus 1. In that case, I will get a coloring of G with just colors 1 to k minus 1. Right? This will be a contradiction because we started with the assumption that G is a k chromatic. So we cannot have a proper coloring of G with k minus 1 colors. So how do I do that? If you look at the the vertices in A, right? So suppose this vertex is vertex Vi, right? This is Vi, and Vi is colored with color K, right? So I now look at Vi dash, right? Vi dash is the vertex here, and Vi dash is colored with some color, from 1 to k minus 1, right? So let's say that it is colored with color, color J, right? So if Vi dash is colored with color J, it says that because the coloring of G, the entire graph is proper, right? The neighborhood of Vi dash cannot see the color J, right? Which means that the neighborhood of Vi cannot see the color J. So I can actually recolor the vertex Vi with the color J, and I can do this for each of the vertices in A, because A is an independent set. It does not matter whether I give the same color or different colors. And this gives you a contradiction, right? Because we have now a coloring of the graph G where we have used only the colors 1 to up to k minus 1, right? We have just recolored all the vertices which was using the color k, and therefore we made a mistake and assumed that there is a k coloring of the graph G star. So we start with assuming that I should have changed the G star instead. We should have so we start assuming that the graph G star has a proper k coloring. Let us call it as color coloring G, right? It's a function, and we will assume that the vertex W is colored with k in the coloring G, right? And on the vertex at V dash, which is an independent set, we have used only the colors 1, 2, etc. k minus 1, right? Because W is in the neighborhood of each of the vertices, right, in V dash. Then we pick the set of all vertices in the graph G, which is colored with the color K, right? So if there is no K, then of course we already have a contradiction. We have a coloring of G itself, right? You just remove the remaining vertices, you will get an induced coloring, right? The coloring which is appearing on the vertices as it is, which will be a coloring of G itself. So just by removing these things, we can always do that. So there are some vertices which are colored K. I am going to recolor these vertices with the color which is appearing on. So if Vi is the vertex colored K, I will take Vi dash and look at the color of Vi dash, which is from 1 to k minus 1, and use that color to color the vertex Vi also. So this I do, and then I will end up in a coloring of G with use at most k minus 1 colors, which cannot happen, and therefore it's a contradiction. So formally writing it, so define A to be the set of all vertices in V, right? V means that vertex set of G, right? Thus that G of the coloring G of V equal to K, and because it is one color, A is an independent set. Then recolor Vi with G of Vi dash, and since Vi dash is not adjacent, and neighborhood of Vi contains a vertex X if and only if it is in the neighborhood of Vi dash. The coloring also remains proper in G dash, okay? And G star. And then delete the vertices V dash and W to get a k minus 1 coloring of G, which is a contradiction. So we prove that the Mycielski construction gives a graph whose chromatic number is one more than the chromatic number of the graph that we started with. And if the original graph is triangle free, the new graph is also triangle free. Okay. Okay, so here is another definition just to give you some questions to work with, maybe not discussing much in this at the moment. So a graph is said to be color critical or k color critical if the chromatic number of G is actually equal to k, and for every edge in the graph, if you remove that edge, the chromatic number of G minus E is equal to k minus 1. So every edge is critical, right? So if you remove any edge, chromatic number decreases. If you have all the edges, then the chromatic number is equal to k. So such a graph is called k color critical or k critical. Now here is a fact that you can try to think about. Right? And then if G is the k critical graph and E is equal to xy is an edge in the graph, then in every k minus 1 coloring of G minus E, the vertices x and y must receive the same color. Because if not, then adding the edge will not create any issue. That is what. Just this observation, you might need it later to prove some questions. Now here I want to look at a very different direction, that we want to look at orientations of a graph. So given a graph Z, we already know that we can define a directed graph from this by giving some arbitrary orientations to the edges. Right? Every edge I can say that okay, xy is an edge. I can either make xy as an arc or yx as an arc. So which means that I get an oriented graph. And so here is a graph G, and you take the orientation of the graph G, which I denote by G with an arrow on the top, right? So oriented G. Now, if I take an oriented G, then I look at the longest oriented paths in the graph, right? So look at the oriented or directed path. So if you look at the directed path, take the largest one and look at the number of vertices in this path. Right? So length of the path is precisely the number of edges, but here we are looking at the number of vertices, which means that it will be exactly one more than the number of edges. Right? So if you look at so d of G oriented is the number of vertices in a longest directed path in the specific orientation of G, right, which is G oriented. Now, if this orientation differs, then of course this D can also differ. Right? So we can have different orientations of the same graph where the the longest path is of different length. Right? For example, I can have something like this. I can have some. Right? So in this case, the what is D of G oriented, which is actually equal to 2, right? Because if I go from here to here, I cannot continue that for any thing. So it's actually equal to the longest directed path is an edge, and this is actually equal to. On the other hand, I could have a different orientation. Let's say I have an orientation like this. And in this case, I have 1, 2, 3, 4, right? 4 in the. So in this new orientation, it is actually 4. Right? So it can differ from orientation to orientation of the same graph. Okay, now here is a very interesting result. The chromatic number of a graph G is actually equal to the minimum over all possible orientations of the graph, right? This D of that orientation. So look at the longest directed path in each orientation and find the minimum among all possible orientations, right? And this length is going to give you the chromatic number of the graph. Right? So one can be a little. It doesn't seem any natural relation, right, between the orientations and the chromatic number. So let us try to see why this is and try to prove this. So how do you go about proving something like this? Any suggestions you have? I would be interested to hear. Okay, so can anybody try to give an idea, right? At least an inequality in one of the directions, right? So, like for example, can you show that the chromatic number is greater than or equal to this, or less than or equal to this? One of, right? Okay, so I will give you a hint. So suppose you have a graph G, right? You want to show that the chromatic number is, is let's say greater than or equal to the minimum overall orientation. So one way you can try to do is that you take the graph G, first of all give it a coloring using the chromatic number. How can you define an orientation to make sure that this property is true, right? I could not hear you. Yeah, so I said that no, to show that let's say that suppose first we will prove that the chromatic number of G is greater than or equal to this minimum overall orientation G of G, right? So so to do this, greater than or equal to or less than or equal to, right? Yeah. So let's say uh, let's say that you start with a coloring of the graph G and try to come up with an orientation, right? And show that this is the this is greater than or equal to the minimum overall. Okay, so orient an edge from the vertex of lower color to yes, precisely, yeah. So what does this tell us? So Nishang is saying that once you start the coloring of the vertices, you are going to orient the the edges, right? So if xy is an edge in the graph, right? An edge in the graph, we know that x and y in a proper coloring must get different colors, right? So the colors on x and y will be, one of them will be smaller than the other. So then if x is having the smaller color, then I will make the orientation from x to y, right? And if y is of smaller, of color, I will make the orientation from y to x. So suppose I do this, then what can you say about the the d of g oriented, right? So what is the what is this d parameter? So the length of the right the maximum directed path in the graph. So if you take any directed path, we know that any edge is actually going from a lower index to a higher index, right? So which means that if you are looking at the paths, the path can never be more than the chromatic number of the graph plus 1, right? If the chromatic number is k, the path cannot contain more than k minus 1 edges, right? Because I start from 1, or like the best case is like start from 1, then go to 2, 3, etc. up to k, right? I cannot have anything larger than this, because every time I go in a directed edge, I am actually increasing the number by at least 1. Okay, now we want to right. So if you have a coloring using the colors 1 to k, define the orientation as follows, right? UV is an edge in the G, and the color of U is less than or equal to color of V. Then I add UV to the arc of the and orient the edge from U to V, right? So what can you say about D of this orientation? So in this orientation, D of G bar is less than or equal to K, right? Because as we mentioned, we cannot have more than K minus 1 arcs, right, in a directed path. So therefore, the chromatic number is greater than or equal to the minimum overall orientations D of G orientation. Now, we want to now give a coloring using using D of G oriented. Right? If we can do that, then we are good, right? Then we know that it is actually also less than or equal to 0. So how do we do that? So given any orientation, we are going to say that okay, you look at the in this particular orientation, look at the longest directed path, and then I can actually come up with a coloring using that many colors. So how do you do this? Okay, so here is what we do. So we look at a set of a minimal set of R's in the take an orientation, any orientation of the graph you give me, right? I take a set of minimal minimal set of edges whose removal make the graph does not contain any directed cycle. Okay, so what I want is that I don't want any directed cycle in the graph after removing a minimum or minimal set of arcs from the graph. Right? So I keep on removing arcs which are forming directed cycles. One of them remove and then look at the remaining graph, and then keep on doing this and find a minimal subset. Right? There is no subset which will do the job, so I will pick such a set of arcs. And then I will get a graph which I can call the directed acyclic graph, because it's a directed graph and there is no directed cycle, then it's called a directed acyclic graph. The graph as a base graph can contain cycles, but there is no directed cycle, right? So here is an orientation. The first orientation is here at a D oriented one, right? And then here is another orientation. There's some orientation here. This could be okay. Now let us look at this first orientation, right, and see is there any directed cycle. So I see that there is this directed cycle starting from this vertex, let's say. So this directed cycle, and to kill this directed cycle, I need to remove some edge, right? So let us say that I will remove this R. Right? I get the remaining graph, right? Then I look, there is another cycle like this, so I can remove this arc now, right? Maybe, and then I say I still have another directed cycle, so I remove this also, right? Now I get a graph, and if you look around, you will see that there is no directed cycle in the graph. Even though there are several cycles, there are no directed cycles. Okay. On the other hand, here you have another graph, right, with another orientation, and in this orientation, these are not directed cycles, and then the only directed cycle is here. If I remove this, I get a graph. Now, once you do this, you get graphs which are directed and acyclic, right? Okay, so take this directed acyclic graph, right, by removing this set of edges, let's say f delta. I mean f origin, right? So it's a subset of arcs. Now what I do is, for every vertex, I look at the number of vertices in a directed path that starts from that vertex. Okay, so for each vertex, I look at the longest directed path starting from that vertex and the number of its vertices, right? I define it as a function, let's say c. Okay? C of x is the length of the directed path, the largest directed path starting from the vertex x. So for each vertex, I will define this. C of x is the maximal number of vertices in a directed path starting at this vertex. And then I'm going to color the vertex x with this parameter, right? So the length of the maximal path starting from that vertex, right? Maximum path starting from that vertex. I mean, not length, the length plus 1 actually. This is the maximal number of vertices. And this parameter d of g, oriented is an upper bound for this number, of course, right? And we know that we are going to use only colors starting from 1 to at most, let's say, d of g oriented, right? Now, I want to show that this coloring, right, that I have given is actually a proper color. Right? So we color the vertex x with this number that we obtained, right? The length of the length of the longest directed path plus 1, starting from that vertex, and claim that this coloring is a proper color. So can you tell me why this is a proper color? So there are two cases here we need to consider, right? So see, to look at a coloring and say that it is proper, all you have to show is that adjacent vertices get different colors, right? So what are the edges in the graph? So the edges in the graph will be either from the edges that we have removed, right, from E cap, which is edges in f dash, I mean f oriented, or edges in this E minus f, right? So which are the existing edges in the acyclic orientation that we have obtained, right? So either of these two are going to be the edges in the graph that we have, right? Like corresponding to the edges in the graph. So if you show that any pair of them, right, will always get different colors on the. So in any such arc will get different colors on its vertices. Then we are done. Right? So we want to show that. Now we know that if an arc, right, is let's say xy, right, xy is an arc, then the length of the longest path starting from y will be less than the length of the longest path starting from x, right? Because normal, so if you have a path starting from y, then I can always extend that path by starting from x. So therefore x and y will always have this parameter c of x and c of y, right? C of y will be actually equal to c of x plus 1, right? No, c of x is actually equal to c of y plus 1. Okay? This is greater than c of y. So therefore, whenever there is an arc in in the acyclic graph that we have, directed acyclic graph we know that for those arcs we will get different. We will give different colors to adjacent vertices. So now what we need to show is that what happens if it belongs to the removed arcs, right? So if we have removed some arc, that we have removed let's say UV, right? So we have removed UV. If we have removed EUV, right, which belongs to F, then what can you say? Yes, we have a directed path from V to U, right? Yeah. So there is a directed path from V to U, and in along this directed path, the number must always increase, right? In fact, the longest path starting from V will be exactly the length of this path plus the longest path starting from U, right? So therefore, they will also get different colors in the orientation. So that is the precisely how we do it, right? So if V is an arc in E minus F, then C of U is equal to C of V plus 1. Right? We observed that before. And therefore they get different layers. And if it is in F, then there is a directed path from V to U, right? If UV is an arc, we removed it only because there was a cycle containing, this arc. So that cycle must basically use this arc, which means that it should go from V to U and then form the cycle. And in this case, we know that C of V is actually equal to C of U plus L, whereas L is the length of the path. And therefore, they are again different, and therefore the coloring is perfect. Okay. Yeah. So because yeah. So yeah, that is true. That is true. Yeah. So in the case that we can take that longest one in the if you want. Yeah. So we can take the longest L to be the length of there is a longest, right? Like at least some, right? So if you take the longest one, it is actually going to be equal to. Anyway, we just need they have to be different, but yeah, this is fine. Okay, so that is how it is, and any questions? Okay, I think we finished our time today. So next day we will continue with tomorrow we'll continue with intersection graphs and some other topics.